So I will continue the webinar on the ecotoxicology of cathodic protection by introduce you some results of experimentation on aluminium and the chemical risk analysis for aluminium. Okay. So, as a reminder, the main objective of EcoCap was to define an ecotoxicological threshold for aluminium in seawater compartment. So here you can see the fourth step of the chemical risk assessment following the technical guidance from REACH. So Christelle introduced the fates, the behavior of the release of GACP and the main release of GACP, the aluminium. Nicolas just introduced the question of evaluation of the aluminium levels in some French facade. Now I will present you the assessment of hazard for aluminium by the definition of a PNEC, marine reactor, for this component. So this methodology is based first on a review of all the literature on the aluminium and the ecotoxicology of aluminium for marine water. And this bibliographic review was combined to data acquisition. In EcoCap project, the idea was to also perform some exposure of marine model species to aluminium and to GICP element. So if we just focus on literature, actually there is some water quality guideline value in the literature. Water quality guideline value based on species sensitivity distribution, so the SSD, which estimates the percentage of species affected for a given concentration of chemical. So in the context of EcoCap, the chemical is aluminium. The first water quality guideline value is from Golding et al. And it is proposed for tropical marine species. This water guideline value determine a protection level for 95% of tropical marine species at 24 micrograms per liter of total aluminium. Another water quality guideline value was determined by Van Damme, and it was for temperate marine species, and the protection level for 95% of temperate marine species was estimated at 22 micrograms per liter of total aluminium. So this two water quality guideline wasn't used during the EcoCap project. The main reason is that the quantity and the quality of data used for this study from the two studies do not meet the eligibility criteria for applying an SSD approach under the REACH technical guidance. So consequently, these threshold value were not considered in our chemical risk assessment, but the data used for determine these two water quality guideline value were considered in our risk assessment. So the PNEC, based on rich technical guidance described by ECHA, so the European Chemical Agency, the PNEC is defined as the lowest value, so ecotoxicological value from aquatic toxicity studies. These values are effect concentration, lethal concentration, no observed effect concentration. So an effect concentration, for example, for EC10, an effect concentration at which 10% effect is observed compared to a control group. So this lowest value has to be divided by an assessment factor. The assessment factor is very important for the PNEC definition because with this assessment factor, you will adjust some experimental data considering uncertainties and variabilities inherent in ecotoxicological assay. So as you can see in the table, several assessment factors can be applied to determine a PNEC, and the lower the assessment factor is, the less conservative the PNEC will be. So the assessment factor will depend on the quality. So if you've got several chronic assay on several trophic level, and if you have also a quantity, a sufficient quantity of data available, you can apply the lowest assessment factor. So one of the aim of the EcoCap project was to reduce the assessment factor in order to make our procedure of chemical risk assessment. For that, we use data from literature, but as I mentioned earlier, we also conduct a series of acute and chronic laboratory experiment to define this PNEC aluminum for seawater. So exposures were performed using aluminum salt on representative model species from various taxonomic groups, as you can see on my screen. We also target representative trophic level, and depending on the model species, we also focused at different life cycle stage of the model, from early life stage, such larvae for the decapod Palémon elegans, as you can see, to adult stage. So here I will just introduce you some results from aluminum salt exposure. You have to know that we perform in parallel some exposure with a water containing a degradation of GACP, so mainly aluminium, but also zinc and other trace elements. Here I just focused my presentation on the chronic lab experiment. So we perform this chronic lab experiment for aluminium on 5 model species, from the model fish marine Medaka oryzias melastigma to to microalgae, so the model strain in ecotoxicology, Phaeodactylum tricornutum. You can see some endpoints. Just to let you know, one of this experimentation is already available in literature. It's the Oryzias melastigma exposure for aluminium. So the scientific paper is available with Mélanie Blanc-Legendre studies. So if you want to have more details on this model species, I invite you to read this paper. So we've got 5 chronic lab experiment results for on various trophic level, and as you can see with this table, we've got 3 species representing 3 trophic level: algae, crustacean with the decapod, fish with marine Medaka, and we've got also 2 additional marine taxonomic group, one on an echinoderm species, so the sea urchin Paracentrotus lividus, and one on the mollusk, the cephalopod, the cuttlefish Sepia officinalis. So thanks to this study undertaken in the EcoCap project, we can reach the assessment factor of 10, so the lowest level in the methodology of the PEG definition for water column without using the SSD approach. Now, based on the definition of the PNEC, we have to find the lowest value in the literature. The lowest value was described for diatom, microalgae, Ceratonis clusterium. 3 studies were focused on the inhibition concentration of this microalgae strain. The first study determined an EC10 at 14 microgram per liter of total aluminium. The second one at 16 microgram per liter of total aluminium, and the last one at 80 microgram per liter of total aluminium. If we do the average of these 3 studies, we arrive at 37 microgram per liter of total aluminium. If we apply the assessment factor, so the assessment factor is 10, so if we divide this lowest value, average value, by 10, we arrive at a PNEC seawater for aluminium at 3.7 microgram per liter of total aluminium. So now we just determine the PNEC. We can now perform our risk characterization for this element in the seawater. So as described, we've got our PNEC. Nicolas Michelet introduced the question of peak for our risk assessment. So we've got the peak considering only aluminium from aluminium input from offshore wind farm. So it's we call that the peak offshore wind farm aluminium, and the peak cumulated of aluminium. So this value corresponds to the maximum concentration of total aluminium within an offshore wind farm. And in this peak cumulated, we consider several inputs, not all the inputs, but several inputs. The inputs from GACP, so the input of the offshore wind farm, but also the river input, and a kind of ambient concentration of aluminium in the area. Just to have before to have a look on our results, you have to note that here I will produce you some hypothetic scenario, case study scenario when all our configuration of offshore wind farm are protected with GICP. So, for example, the offshore wind farm in the Seine Bay in our configuration is protected with GICP. In reality, the offshore wind farm in the Seine Bay will be protected by ECCP. It's the same for the Saint-Nazaire offshore wind farm. Just to keep in mind this element. Also, as Nicolas Michelet mentioned earlier during his presentation, we are in a worst case scenario for water column. So we consider that all elements released by GICP stay in the water column. There is no interaction with suspended matter, no potential accumulation around the foundation of the wind turbine. So all elements from GICP stay in the water column. Also, for our peak, as a worst case scenario, we also consider the maximum concentration reported by the modeling approach. Now we can look at the results. So Nicolas mentioned this result later. So in my presentation, I just keep results from the Seine Bay offshore wind farm, Saint-Nazaire offshore wind farm, and the two Golfe du Lion floating offshore wind farm. As you can see, considering only the aluminium input from offshore wind farm, the level of concentration remain below 2 micrograms of liter of total aluminium in the water column. And the level of aluminium in the water of the offshore wind farm, considering all, not all, but additional aluminium inputs, can reach 22 micrograms per liter. And by making a very simple ratio between PEC cumulated and the PEC offshore wind farm, you can have information on the relative importance of the input of the aluminium from offshore wind farm, and this is quite blatant for the Saint-Nazaire, the theoretical Saint-Nazaire configuration, and you see that the PEC cumulated is mainly driven by riverine inputs. So now we can perform the formal risk characterization, so the ratio between with PEC offshore wind farm on PNEC, and considering only only the aluminium inputs from offshore wind farm in our configuration, there is no case that exceed the risk index of 1. But if we consider other aluminium inputs, as you can see, we can present you a risk for the water column with aluminium under our specific condition of scenario. There is no risk for the Seine Bay offshore wind farm, but for the Saint-Nazaire offshore wind farm, there is a risk. As I mentioned earlier, the main driver of this risk, it's the river inputs. The Saint-Nazaire offshore wind farm is just in front of the Loire River plume, and river such Loire has quite high aluminum concentration, and we can have this result due to this Loire River. For the two configuration of Golfe du Lion area, the main driver of the risk are the atmospheric inputs. So the 4 microgram per liter that we use in our PEC cumulated for the ambient concentration, and this ambient concentration is mainly due to atmospheric input. So to keep in mind, the main results of the ecotoxicological assessment of GICP during EcoCap project, the threshold value evaluated in the context of EcoCap ecotoxicological experiment are all higher than the projected aluminum concentration determined by EcoCap modeling approach. So it's the first bullet point. So I'll talk about the lab experiment performed during EcoCap projects. If we consider the more normative risk assessment based on the REACH technical guidance, there is no expected risk for aluminium in water column in our scenario, but this risk appears for some configuration when all potential input of aluminium is considered in a cumulative way. And finally, as Christelle Kapla mentioned earlier during the presentation, to fully exclude any environmental risk associated with GICP, aluminium GICP, several issues need to be addressed. The major challenge will be to address the interaction of chemical from GICP with suspended matter, studying the potential accumulation of these elements in the sedimentary matrix, investigate the bioavailability of this element in water column, but also in the sediment. And if you want to perform a risk assessment for sediment for aluminium and GICP component, there is a lack of data, of ecotoxicological data focused on the sedimentary matrix. Additionally, some trophic investigation on this element must be addressed, and also sublethal assessment. During the EcoCap project, we follow some chronic and acute assay with unrealistic aluminium concentration, and we focus mainly on endpoint very strong, as I can say, such mortality or reduced of growth. The idea is to perform more sublethal assessment for this question of GICP release. And on GICP, as you know, there is aluminium, zinc, but also other chemical elements. Future work should focus on these elements, and particularly indium and gallium. Focus also on the cocktail of elements. And if you want to investigate the question of potential cocktail effect of anode, you have also to consider other chemicals, so endogenous chemicals from the offshore wind farm activity, anti-corrosion coating, for example, but also chemicals from outside the park. So exogenous chemicals must also be considered in cumulative chemical risk assessment. So thanks for your attention. Now I will let Jean-Luc Bouden introduce the question of ECCP.